Hi, Sam Roberts here from Roberts Geospatial, Part 6 of the Coorabulka Vegetation Index study using ProRaster Scientific, which you can purchase very cheaply on the Microsoft Store from home. So we've computed statistics, and one of the outputs from the statistics operation is a CSV file. That's a comma delimited file. You can load that straight into a spreadsheet. So here I have a whole bunch of spreadsheets. So the first one here is mosaic. So this is the original mosaic sequence. So we have all the cloud in this data and everything else. So what you get in your statistics from a sequence is you get one row for every time point in that sequence. So we've got a total of 49 rows representing 49 time points over that whole year from the 9th of July through to the 28th of July 2023. So I'll just show you what these what you get in this CSV file. So you'll get the field index and the band index from the raster. You'll get the start time and the end time. Now these are programmers' numbers. This is a number of seconds since midnight, January the 1st, 1970 or something like that. It's a programmer's number. Over here is a start time and end time in a readable format, so this gives you the date and the time, and over here you just get the date, and they're useful for annotating your graphs. So it's the first and last event index, although in these sequences the first and last event index are always going to be the same, and then the field name, the band name. Over here the resolution at which the statistics were computed, the resolution level, so we computed it at the base resolution level, which was 0, and that corresponds to a certain cell size, and here's the cell size reported here, 30 meters by 30 meters, giving a cell area of 900 square meters. Stats mode was spatial. Now here's the all-important sample counts. So the total number of samples in the data set is firstly reported. That's your sample count, and then you have the total number of valid samples in the data set. Remember that we're clipping here to the Coorabulka polygon. A valid sample is a sample that's got data in it that isn't null, that is valid data. Then you have the number of invalid samples in that data set. So if you add 7 million to 5 million, you'll get 12 million. So they add up. And then over here we've got some more information about why samples are invalid. So the first channel is invalid number count. That means that the number itself was an invalid number, like it was negative infinity or something like that. Well, we don't have any of those numbers in this data set. And then over here we have empty samples and we have null samples. Now remember that I said to you in one of previous videos that it's always a good idea to put your polygon clipping last and then compute your statistics. That's because you get some information in this empty and null samples columns. So the empty samples are samples that are invalid, don't have any value in them, but are inside the polygon. Whereas the null samples are the samples that are invalid and are outside the polygon. So so we can see here that we expect, this is how many samples we expect in the polygon, about 5 million. So in this event, which is cloudy, we have 1 million valid samples, and then we have 4 million empty samples. So they're invalid samples, cloudy, inside the polygon, and then 1 million that are valid. And all these null samples, the 7 million, which when you add to the 5 million makes the 12 million, they're samples that are outside the polygon. So you can use that information to sort of do a percentage, give you a confidence measure of your data based on how many samples you got in the polygon. Now if you multiply those sample counts by the area of a cell, you'll get all these columns. So you have the sample area, valid sample area, or total sample area, valid sample area, invalid. So these things just match those columns I just spoke about, multiplied by the area of a cell. So then we get the actual statistics data. So this is our summary statistics. So the minimum value in the data set, the maximum value in the data set, and the mean or average value in the data set. Then we have the variance and the standard deviation, the signal to noise. Then we have the information derived from the histogram distribution. So I have our lower quartile at 25%, we have our upper quartile at 75%, our interquartile range, our median, which is at 50%, and our mode, which is our most frequently encountered value. And then we have that skewness measure, indicating whether the histogram is skewed to the right or skewed to the left. And then we have our spatial cell-to-cell statistics, so the minimum value, maximum value, mean, variance, and standard deviation. These are numbers which tell you, which record how the data values are changing from one cell to the next. Might be useful in some circumstances, but probably very limited circumstances. So that's our spreadsheet. You can either load this CSV file straight into something like Excel, or what I usually tend to do is just load it into a text editor, copy and paste, and then you can paste it into Excel using the comma delimited import scheme, and it comes in nicely, and you can put them all into separate sheets. So I've done that here, and we've got our mosaic sheet, then the data for our collated mosaic, which was almost exactly the same as mosaic, and then we have our collated mosaic with 3 time points, so one before and one after the time point of interest, collated mosaic for 5 time points, and then remember I clipped out the NDVI below 0.15 and I computed statistics for that, so we have that spreadsheet as well. So let's graph these things up. So so we're looking at a valid cell count here. So the yellow line is the valid cell count for the collated 5 time point series, and you can see that it's pretty much static. Little dip there, but basically it fills up every pixel with valid data at every time point. If you go back to collated X3, that's this grey line, you can see that there's just a couple of places where it hasn't done as good a job as the 5 time point series, but mostly pretty good, whereas this blue series is the mosaic, and you can see that when you do have cloud, this is 0 valid samples here, it drops pretty much all the way down to 0 a lot of the time. If there's any cloud, then it tends to be very destructive and you get almost no valid data. So that mosaic is hard to get good statistics from, whereas the collated by 5 time point mosaic will give you very consistent statistics. So that's our valid cells. From now on, we're going to be looking at the data for the collated 5 time point mosaic sequence. So let's look at the minimum and maximum values. So let me do a zoom. So here we have the minimum value down here in red, and the maximum value up here in grey, and in the middle is the mean. We'll look at the mean a little bit later. So firstly, the minimum value tends to bump along. Actually looks as though it's in continuous decline, slight decline. So this is you're looking at bare earth here on the minimum value, and it does look as though that the dry areas outside of the channels are continuously drying out over the period of this year. There perhaps hasn't been any significant rainfall at the station itself. And so we're seeing a continuously declining minimum value in the vegetation index. Looking at the maximum value, so at the beginning, a year ago in July, they had relatively good vegetation at the station. It declined continuously until the end of the year. And remember, at Christmas or January in 2023, we get our first flood event. And then we see vegetation start to pick up. It picks back up to this maximum value around 0.8, and then it remains there for the rest of the entire series, indicating, of course, that good vegetation has returned in that in that Channel Country area. I have to do a zoom again. So zoom. Okay, so here we're looking at the lower quartile and the upper quartile and the median value. So same sort of story with the lower quartile that we saw with the minimum. It really bumps along, does start to pick up a little bit towards the end here, but you know, it's pretty static, if not somewhat in decline. Looking at the upper quartile, so this is the value at which 25% of the data is more than this value. So with a higher value, we're obviously looking at higher levels of vegetation on the station. So we start out reasonably high, around 0.19. It declines continuously and then bumps along until Christmas. We get our first flood event. It rises substantially. We get a flush of vegetation. Our second flood event wipes it out. But it bounces back quickly up to this peak in towards the end of May in 2023, and then it begins to quite rapidly decline again over the remainder of the study period towards as we go from summer or from autumn into winter. So here we have the mean in blue, the average value, the median and the mode also shown in yellow and in red, orange. So the mean value gives us a story. So again, we have good vegetation at the beginning of the series. It continuously declines until we get to Christmas. We get a flood event, which takes out whatever vegetation we have left in those channel countries, and then the vegetation, you get a flush. Here's that second minor flood event in February, and then you get this third flood event at March, April, which takes out the existing vegetation again in the channel, but it bounces back and comes right back up, and then we have high levels of a nice high mean vegetation index for the rest of the period. Looking at the mode, remember, is the value that's most likely to occur in the dataset, and you can see that it's pretty much, well, it's kind of flat, really. It doesn't do much at all, and that reflects the fact that the eastern areas, where a kind of desert country, are pretty much static over this entire year. Most of the signal is coming from the desert country, because it's more than half of the area of the station, and so that mode value remains pretty much static throughout the entire series. But the median does deviate from the mode. Here you can see it's rising up and coming down, and that's telling some story. I've got that plotted up here, where we're looking at the deviation of the median from the mode. So this is going to be, it's just a formula. I better zoom to it. It's just median minus mode divided by the mode. So so we get a big deviation in that over that time where we have flood, and then it starts to drift back towards zero as the whole system starts to even out. This is the skewness. View, where's view? Here, zoom to selection. So this is the histogram skewness. Remember, at 1, it's symmetrical about the mode. So where it's greater than 1, it means we're getting vegetation, and when it's less than 1, it means we're getting less vegetation. So we start off greater than 1, but it declines continuously and then goes negative. And goes negative until the end of the year, and then we get that flood event. And the flood event actually takes out whatever vegetation we had, and we get a big negative skewness, indicating that we've got much more bare earth. We're looking at the ground, we're looking at mud, and in this case water. But it bounces back, comes back up to 1, and then starts to increase as the vegetation grows. And then we get that second big flood event, takes it out again, bounces right back, and now comes back up to a higher level with a histogram skewed to the right, indicating that we've got higher vegetation values in our distribution. Here's the standard deviation. So the deviation is standard deviations, sort of measuring how tight the data is clumped around the mean value. Or we start off. So if the deviation is larger, that means we're getting more values that are either very high, so another good vegetation, or very low, like water. So we start off with vegetation. It's in continuous decline for the entire year, starts to sort of bottom out. Then we get that flood event, which gives us a high deviation because we've got some very negative values away from the mean. That drops down, and then we see a story of slowly climbing standard deviation as the vegetation develops, punctuated by this second major flood event, which again gives us a spike in our deviation, and then it slowly increases up to a maximum, and then is looking as though it's starting to slowly decline again towards the end of the study period. So I've got a map here called vegetation biomass proxy. So now we're trying to relate the vegetation index to the vegetation biomass, from which you might be able to compute what the carrying capacity of your cattle station is over time. And so there's going to be a relationship between vegetation index and between biomass, and I think most scientists would probably agree with that. I think that's a reasonable statement. I'm not exactly sure what that relationship is. I'm sure people have probably studied it, but I haven't looked up that literature. But I'm sure it wouldn't be static. It probably varies depending on where you're doing your study. So for a tropical rainforest, it might be quite different to this dry rangeland kind of study. So I've got 3 curves here with different relationships between vegetation index and biomass. And I might I'll go back to this, just show you the formulas that I used to compute. So here is the linear formula. So I've got linear, I've got log, and I've got power. So with a linear relationship, I assume there's a linear relationship between vegetation index and biomass. So as vegetation index increases, biomass increases in some linear fashion. With log, I'm assuming that as vegetation index increases, the increase in biomass actually starts to increase slower, so it tends to tail off. With the power, it increases higher, faster. as the vegetation index goes up. So that's the three possible models, and I've just got some simple formulas here where I've implemented those, modelling them against just the mean value. But what would be better would be to model these against the actual histogram distribution, row by row, and then sum up all the values in order to get an accurate biomass reading, or a biomass proxy. I think I might add that into the statistics as a standard function, where you can give it some kind of relationship between your index and your proxy, and it will compute and give you some data. So looking at this linear relationship, for example, so here we're looking at our biomass proxy. So over that period, maybe I'll zoom in. Can I zoom to that? Yeah. So over that period, we had biomass continually decreasing, reached a minimum, bumped along as we went through the beginning of summer until the end of the year, and then we had our flood events, and it started to rapidly increase. We had this second flood event, minor flood event, that took out existing vegetation, bounced back, and then we had the second major flood event, which damaged our biomass substantially, but it bounced back and came back up, and then started to decline again over the remainder of the year as the station started to dry out once more. What can I do? Scroll over. So this one would be this is the logarithmic one, and you can see it's sort of similar story, but as we get this vegetation at this end, where we've got vegetation in the channels, it's just not as valuable because it's logarithmic relationship. And here's the opposite, where we have a power relationship between biomass, vegetation index, and power and biomass. And so here, where we have this more lush vegetation in the channel country, we're getting much higher biomass. So that's something that you would fiddle with. Probably the person who owns Coorabulka Station would look at this and say, well, I can tell you exactly what it is because I've been out there and I know what my I know what my carrying capacity is, and they could give us an indication of what this actual relationship is. Anyway, so that's the end. Thank you for watching, especially if you've made it all the way through. It's been a big study, lots of fun for me. I hope you found it interesting, and I hope that it gave you plenty of insight into what you can do with ProRaster Scientific. So thanks for watching. Bye.